Welcome to this joint ISN-KDIGO webinar on sustainable dialysis, challenges, solutions, and future directions. I'm Jenny Flythe, a nephrologist at the University of North Carolina. I'll be moderating today's session. We're glad you could make it. The webinar offers subtitles in numerous languages. It's being recorded and will be available online at the ISN Academy. We've left some time for questions at the end, so please submit questions during the webinar, and we will discuss them following remarks from both speakers. Dialysis is one of the most resource-intensive medical interventions, driven by its high water and energy consumption, heavy reliance on single-use plastic consumables, and frequent long-distance supply shipping. This webinar will build upon discussions from the spring 2025 KDIGO Controversies Conference on green dialysis, with the speakers summarizing current challenges and offering potential solutions, both short and long term. We have two fantastic speakers with us today. First, Dr. Katherine Barraclough will provide an overview of the topic and identify changes that can be made in current practice. Dr. Barraclough is a nephrologist from Melbourne, Australia, who is affiliated with the Royal Melbourne Hospital and University of Melbourne. Her research interests lay at the intersection of planetary and human health and environmental sustainability within the healthcare system. She was the co-chair of the KDIGO Controversies Conference on Green Dialysis and is a current member of the ISN's Green K Working Group. Dr. Barraclough will be followed by Dr. Winston Fung, who will discuss future directions and innovations. Dr. Fung is a nephrologist from Hong Kong who is an associate consultant at Prince of Wales Hospital and an honorary clinical associate professor for Chinese University of Hong Kong. He has research and clinical interests in sustainable kidney care. He's a member of the ISN Emerging Leader Program and member of the ISN Green K Steering Committee, as well as the lead author for the International Society of Peritoneal Dialysis position statement on sustainable peritoneal dialysis. Dr. Barraclough, please get us started.
Thank you, Jenny. I'll just share my slides. Thank you very much for the introduction and to everyone for coming along this evening for me. These are my disclosures. Just to start with some background, I suppose, rationale for why KDIGO and we felt that this was such an important topic for a KDIGO Controversies conference. As I presume most attending tonight will be aware, we are faced at the moment with converging environmental crises, and collectively these pose really significant and escalating threats to both global and kidney health. The flip side to this, though, is that healthcare has a really significant environmental impact in terms of carbon emissions, water usage, waste generation, pollution. As Jenny mentioned, dialysis is probably the most resource-intensive medical therapy on a recurrent per capita basis. And so because of this, looking at ways that we can reduce the environmental footprint is really important. So there is an ethical imperative, there is, particularly in some parts of the world, an emerging regulatory imperative, and there's also a practical necessity. So if we want to maintain the quality of care that we're providing, ideally improve it, and increase access to dialysis for the increasing number of people needing it, we need to take heed of the resource constraints that exist and improve the way we deliver care from an environmental perspective. There have been great things done around the world already from a green dialysis perspective, but there has been relatively piecemeal implementation. And what we really need to see is widespread adoption of the good things that are out there. We also need new technologies and models of care, because whatever we do to fix up the way we deliver care, the technologies and models that we have at the moment will always be to some extent resource intensive. So with all of this in mind, KDIGO held a Controversies conference in April last year focused on green dialysis. As is always the case for KDIGO meetings, there was global representation and there was cross-disciplinary representation. So as well as the usual doctors, nurses, always patients, we had engineers, dietitians, we also had some procurement experts and environmental scientists. There were some cross-cutting themes that really infiltrated through all discussions. And the first of these was that healthcare sustainability, which we defined as the capacity of a healthcare system to deliver care both now and over time with consideration for future generations, so when you consider healthcare sustainability, it must be recognised as a key domain of quality healthcare. So when you have quality healthcare, it must be safe, it must be efficient, it must be effective, but it also has to be environmentally sustainable if you want to maintain that quality. We agreed that healthcare sustainability should be measured, considering patient outcomes relative to the triple bottom line of environmental, social, and financial impacts. You'll notice that when you look at the equation that's at the bottom of the slide, patients are very squarely positioned as at the top of the equation, but then recognising that there are broader impacts that impact the value that we provide. Participants applied life cycle thinking in all discussions. And so what this involves is thinking about the impacts of a product of a service or a service throughout its life cycle, from the time that you extract raw materials to create a product, all the way through the use phase till you reach disposal. We were tasked with two main things, and the first was to think about ways that we can optimise existing clinical and operational processes, and the second was to think about innovations that we need to see. So I will talk for the rest of my talk about the first part, how we optimise what we have in place now, and then Winston will go on to talk about innovations. So the list of things on this slide is the range of things that we considered during the course of the conference, and I'll go through, pull out some of the main things that were discussed in each of these areas. The first part of the discussion was to do with dialysis prescriptions, and I suppose at the outset it was recognised by conference attendees that if you reduce either the length or the frequency of dialysis, you're very likely to, or almost certainly you will reduce the environmental impact. That said, taking into account the principle of value-based healthcare that I talked about before, there was very much emphasis on the fact that any change in prescription or treatment must not only maintain but ideally improve patient outcomes. We identified optimising the timing of dialysis initiation and adoption of incremental PD as ways that we can improve environmental sustainability without compromising care in any way. What is known from RCTs from a good while back is that there's no survival disadvantage with later dialysis initiation. And so because of that, most guidelines recommend commencing dialysis only when clinical indications arise and not at any particular level of GFR. I think this is something that is already quite widely implemented, but important to keep it front of mind because of the patient, environmental and economic benefits that come from this. In terms of incremental dialysis, what is known in the case of PD is that it achieves survival outcomes comparable to standard PD regimens in appropriately selected patients. It also leads to potential benefits in terms of residual kidney function, preservation of residual kidney function, and quality of life. Because of this, incremental PD has been endorsed by the ISPD, and over the last 5 or more years, there has been a really major uptick in incremental PD prescribing. That said, there is still very variable practice amongst centres and scope for expansion of this. For incremental hemodialysis, there is also substantial evidence that it achieves equivalent outcomes, not to the degree that there is with incremental PD, but a growing and relatively good evidence base. And it is likely that it provides the same sort of benefits in terms of quality of life and residual kidney function. Despite this, the adoption of incremental hemodialysis has been much slower than for peritoneal dialysis. And there are probably a number of reasons for this, not least the fact that in-centre dialysis involves quite rigid, in many cases, scheduling. Also, probably the not quite as strong evidence base is a factor. We discussed the fact that to increase incremental dialysis prescribing, clinician education is really important. It will also be aided by decision support tools, and guideline development was thought to be a very important factor also. The ISPD guidelines have done a lot for pushing incremental PD prescribing forwards, and so as more and more evidence comes forward, I think a guideline in the hemodialysis space will be really helpful as well. And as mentioned, the issues of dialysis scheduling can be difficult, and so that's something that needs attention as well. We talked about diet. So most, I'm sure, on this call will know that plant-based diets almost universally deliver environmental benefits. So this is in terms of carbon impact, biodiversity, land use. If you have a plant-based diet, it has a lower impact than animal-based diets. When looking specifically at patients with CKD, there are a number of cohort studies and small RCTs that show that plant-based diets lead to a range of benefits as listed on this slide. And because of these studies, the 2024 KDIGO CKD guidelines recommend that plant-based eating is prioritised over animal-based foods. Extending this into the incremental dialysis space, there is a number of studies that have looked at combining dietary modifications, so more plant-based diets with incremental dialysis, and they've shown that it can be an enabler in the incremental dialysis space. We looked at the issue of dialysate flow rate. So back in the 1960s, with old dialyzers, it was assumed, it was when we had the dialyzers that were in use back in the 1960s, it was important that high dialysate flow rates were used to achieve optimum clearances. But over time, there have been significant improvements in dialyzers, such that the relative importance of maintaining a high flow rate is very different now. Despite this, around the world, almost universally, dialysate flow rates are maintained at 500 or higher in some places. There have been those studies looking at whether these dialysate flow rates are needed to achieve adequate solute clearances. And studies that have been conducted have shown that when you compare dialysate flow rates of 700, 500 down to 400, there are very minimal and clinically insignificant differences really in clearances, blood pressure, weight gain, and other biochemical parameters. An issue with these studies is that most of them are short-term. There has been one long-term study that followed patients out to 2 years. They were patients with low body weight, but this showed, again, equivalent adequacy and also equivalent survival with a dialysate flow rate of 500 compared to 400. The water savings that occur with this per treatment are not huge, but when you extrapolate these out for the number of treatments and the number of patients on dialysis, there is the potential for really large water savings. The consensus from the conference was that a dialysate flow rate of 500 was a pragmatic upper limit for routine care. That said, it was felt to be very reasonable to consider a lower dialysate flow rate on an individual basis, taking into account, for instance, things like achieved blood flow rate and patient size, provided solute clearance and other outcomes could be closely monitored. There was also agreement, though, that long-term studies were needed to make sure that, in the longer-term outcomes were similar. In terms of hemodiafiltration, again, as most people will know, what this does is combines diffusion with convection. The diffusion is for solute clearance. The diffusion is achieved by applying typically the same dialysate flow rate as is used in dialysis, so 500 to 800. Convection is achieved by high ultrafiltration, and because of this, you need to infuse a substitution fluid. When hemodiafiltration is practiced in this manner, total water usage increases, as does acid, bicarbonate, and energy demand. But because you have both the diffusion and convection, it follows that you don't need the same dialysate flow rate to achieve the same solute clearance as you would get with hemodialysis. There have been a number of studies looking at reducing the dialysate flow rate in hemodiafiltration as compared to that used in hemodialysis. And what these have shown is that when you do this, you can achieve the same or superior solute clearance for actually less fluid consumption. What the data suggests is that hemodiafiltration may in fact be more resource efficient than conventional hemodialysis. The caveat that was brought up at the meeting, though, was that there are some different consumables required for hemodiafiltration compared to hemodialysis. Because of this, we need formal life cycle assessments to definitively show that hemodiafiltration is a similar or less resource-intensive therapy. Dialysis equipment and operational settings, another thing that was focused on at the meeting. There was universal agreement that at the time of procurement, we should be looking at water, energy and consumable differences between RO systems and dialysis machines. And we should be, in our procurement criteria, considering both environmental as well as cost comparisons or cost savings. One thing that makes this hard in practice is that often the comparative data on water, energy, consumable usage by different RO or dialysis systems is not available. I put on this slide some work that came out of Australia and was presented at our meeting last year, looking at different resource usage by different dialysis systems. And I think we need a lot more of this so that we can make informed procurement decisions. There was also focus on the settings that we apply to our dialysis equipment. The opinion was that RO plant operating hours should be examined and adjusted to make sure that there is no redundancy, that the systems are only on when dialysis is occurring. So the RO plant is very much the biggest energy water usage in a dialysis unit. You only want to be using those resources when you need to. In the same way, very often disinfection schedules exceed what is required, and so examining disinfection schedules and making sure that there is no redundancy is a really simple and cost-free, cost-neutral way of improving environmental sustainability. Another thing that was looked at was the RO recovery ratio. Newer or more modern RO systems have the ability to recover some of the water that is typically sent to the drain after RO filtration. There are ways to gradually increase the RO recovery, taking note of conductivity and fouling of the membrane to make sure that this doesn't compromise dialysis water delivery or membrane integrity, but can lead to really substantial water savings. There will always be water that is sent to the drain when you use reverse osmosis as a water filtration method. Conference attendees agreed that reuse should be universally considered. This said, feasibility will depend on a number of things. One of the main ones is the building infrastructure. If you have old buildings, for instance, with asbestos in the walls, it can be very costly to install water-saving equipment or water capture equipment. But very much whenever there is a new dialysis build, this should be a priority. We also talked about central delivery of acid concentrate. So currently, acid concentrate for hemodialysis is usually supplied in single-use plastic bags or canisters. The alternative to this is centralised delivery from a bulk storage tank and a distribution loop. When you have this sort of system, so a bulk storage tank in the unit, you can either have this bulk concentrate trucked in a big tanker and put into the storage tank, or you can have dry powder delivered that is reconstituted on site. When you have these dry powder formats, there are now systems that can automatically reconstitute it into concentrate, which takes away all of the manual labour that used to be a concern with these sorts of systems. There have been a number of studies looking at the impact of central acid delivery, and what these have shown is that they lead to, again, a really large range of environmental benefits. You have very significant decreases in waste, decreased carbon emissions. There are benefits in terms of storage and manual labour, and also reduced operating costs over time. The big problem usually with central delivery of acid concentrate infrastructure installation is the capital cost, but important to take into account the operational savings over time. And again, when you have a new dialysis build, it should be something that is considered at the outset. One thing that was raised was that bulk acid for central delivery is not yet available in all regions, including Australia. And so engaging industry to assess access gaps was thought to be something that we should all prioritise. We then moved on to consumables. So consumables are the main source of both carbon emissions and waste in both hemodialysis and peritoneal dialysis. There was consensus that it was really important for dialysis teams to audit consumable usage. So what this means is looking at every step of the process, for instance, with hemodialysis cannulation or a PD exchange and see whether there is, again, redundancy that can be addressed to reduce the impact. On this slide is some of the examples from the literature that we presented in our conference report, really simple things that can make a big difference when it's applied across all patients and recurrent treatments. We talked about dialyzer reuse. The first thing that was raised was that most of the evidence about dialyzer reuse comes from old studies, and even in those old studies, results were mixed. There was quite a discrepancy between low and middle income country attendees and high income country attendees with regard to the appetite for dialyzer reuse. Low and middle income country attendees really underline the pros of cost containment and expanding access to treatment that come with dialyzer reuse. In contrast, most high income country attendees were concerned about the potential risks, the operational complexity, and some of the regulations that exist that prevent dialyzer reuse. We had presentation, though, on some of the newer automated systems that are coming into the dialysis space. This is one such system that is fully automated. It uses an environmentally safe cleaning technology. The manufacturer claims no loss in dialyzer performance for up to 40 treatments, and there's been some independent environmental analysis done showing that it leads to reduced carbon, water, and energy usage. And so, the consensus was that there is promise in this space, and probably in the future something we need to think more about. Waste management was the next on the agenda. Really, the low-hanging fruit in terms of waste is effective waste segregation. So clinical waste has an exorbitant environmental and cost impact compared to general waste. And so therefore, if you can effectively segregate waste at the source, you can make a really big difference off the bat. We talked about on-site hazardous waste sterilisation systems. So typically around the world, clinical or hazardous waste is incinerated, and this is really environmentally problematic. These on-site, in-unit sterilisation systems instead use steam or microwaves or chemical disinfection. What these systems do is they enable reclassification of treated waste as general waste, so then when you dispose of it, it's much cheaper and you don't need to incinerate it. The other thing is that if you can sterilise waste, there is the potential to recycle it. This picture on this slide is a waste sterilising machine that we've tried in a unit near me in Victoria, Australia. What we found was that it was very cost effective. It was an expensive system, but there was a return on investment within under 2 years, and that was because converting all of the waste to general waste saved a lot of money. In my state of Australia, we actually centrally steam sterilise waste. So we found that compared to that, the machine was actually not as environmentally effective. But when you compare it to incineration, there were substantial environmental benefits. The last thing that we talked about was building design, and I won't go into this in detail, but there is information in our conference report. It is really important, particularly for new dialysis builds, that there are general sustainability features, that we think about things like solar panels, insulation, greenery around the unit for the sake of patient experience, but also that we build the spaces so that they can house things like central delivery of acid. And that's the end, and I will hand over to Winston.
So thank you, Katherine, for the very great presentations on the first half, talking about what we can do with the existing practices and resources. And so then thank you, Jenny, for the very kind introductions as well. So let me bring up my slide. So in the remaining half of the talk, my task is to focusing on some of the hopefully more innovative approaches to green dialysis and hopefully optimizing some of the strategies. And in fact, as we go through some of the slides, I'm sure you will probably realize actually some of them are so-called innovative, but actually it's quite simple measures, and actually briefly already coincides with what Katherine was talking about, some of the practice changing potentials. So hopefully with that, we have the so-called the future is bright and the future is green. So I've nothing to disclose apart from part of the ISN Green Case Steering Committee as well as the IFSPD position statement as mentioned. So Katherine already mentions KDIGO, because of the increasing importance of green dialysis, we held a Controversies conference in April last year, and with a lot of the different experts across the world, but and also across the different specialties. And with that, we have published the KDIGO controversy conclusions on green dialysis. Welcome everyone to have a read on that. But as I mentioned, my task is to highlight some of the potential innovative approach. So, but before that, I just want to highlight this actually quite interesting concept that when I was in the conference, a lot of the participants was highlighting, and this is the so-called technologies readiness levels. So, and Katherine already mentioned as well, actually there are a lot of works being done for green dialysis, where there is changing the current practices and optimizing some of the current care, but also some of the more innovative approaches and technologies. So there are a lot of various bits and bobs and piecemeal, as we call it, in terms of informations in the literature. So one of the tasks for the participants in the conferences was to highlight some of the innovative approach, but more so whether they are so-called technology ready in terms of being that we can use on the actual practices as highlighted on these scales on the left side. So you can see here in some of the levels as relatively speaking, still kind of very innovative and at the level of research. So they're only experimental in concepts and certainly pilot study, for example, and nothing more than that. But as you kind of go down to the scales, there are things already being validated in the more research settings, in the lab settings, but also in terms of clinical environments, and some of them are even already proven to be operational in actual clinical settings. So with that, we tease out some of the current strategies, whether innovative or not, or some of the newer technologies to see, as you can see on the right side here, highlighting some of the current readiness. So in the remaining of time, I will highlight all of these, hopefully. But as you can see, some of them are, if you look at it, it's actually more kind of practicable. For example, try to capture some of the energy loss through those hemodialysis efferents that's being discarded otherwise. And then, for example, try to consider much shorter bloodlines from a dialysis point of view. And some of these hopefully will be kind of be sooner than later in some sense. So as I mentioned, there are actually quite a lot of innovative approaches and technologies. So given the interest now, I try to go through all of this. And as during the conference, a lot of the participants highlighted. And with that, I'll dive into the first one here, which is the reducing some of the redundancy in consumable. Katherine already highlighted that consumable are some of the actual major contributors in terms of wastage in kidney care, in particular, for example, HD care, but also PD care. There are lots of packagings being discarded, and there are a lot of consumables being discarded, such as gauze. And perhaps in a PD, for example, in a PD care for the care of exercise, we may perhaps only use one gauze, for example, but the whole package is about 5 gauzes. So in which case you will actually have a lot of redundancies and wastage as a result. So there was a lot of discussions on how to minimize some of this redundancy. In particular, there was a lot of participants highlighting on the HD bloodlines. And I'm sure you will realize that when you visit your own hemodialysis center, the patients are being hooked up with the dialysis machines, and there are lots of plastic tubings lying over the actual chair connecting to the HD machines. And some of them can be quite long, and we obviously depending on the potential storage space of the machines as well as the linkage to the patients. But there was discussions of whether we can minimize some of the shortening of the lines, so perhaps with much less usage of manufacturers from plastics, for example. So that hopefully then in a sense that you can add up and build up the less usage of the plastics, and as a result the manufacturing will be the resources being used for the manufacturing will be much less. But obviously there has been study, actually there was a lot of controversy in the sense that there has been study talking that there has been a minimum length for some of the bloodlines, in particular, as you can see at 1.7 meters, because actually there have been suggestions that the shorter it is, there may be the risk of embolizations and as well as the giving the nurses sometimes to kind of notice some of the kind of air bubbles or examples during the transits of the blood through the lines. So obviously there is some controversies in the sense that the length of the bloodlines. So, and certainly a lot of small study clinical-wise has to be done to kind of optimize the length of it. And there also has been some talks about how to optimizing some of the flow, and Katherine already mentions, for example, some of the dialysis in terms of our machines, the kind of the dialysis flow rates, for example. But there have been talks to using, for example, AIs or computational modelings to kind of optimize the flow such that we can minimize, again, some of the kind of wastage in terms of fluid, of water, but also in terms of kind of heparinizations, and by having the flow being much better, minimizing clotting, for example. But obviously, there has been kind of issues with regarding to the use of AI, for example, because I'm sure you know AI actually does require a lot of computing powers. And with that, a lot of electricity, and hence, if the electricity source are not green in a sense, for example, coal and oil productions of the electricity, then obviously that is counterintuitive. So there have been a lot of talks about how to optimizing the flow while bearing in mind the computational modeling may be difficult in a sense if you have to use AI. So from the PD side, there's also participants from the PD groups have been talking about maybe perhaps we can redesign some of the APD cassettes as highlighted on some of the mini pictures here. Because again, as you can see, there's a lot of plastic used. So perhaps if we can redesign the PD cassettes such that they are more renewable and reusable materials, and again, similarly, shortening some of the plastic tubes, some of the plastic linings, that perhaps then we can minimize some of the consumable usage as a result. And certainly there, again, talks of aligning some of the PD bags with more varieties. For example, there have been studies in both Canada, but also in Australia, showing that because for the clinical environment, that's the size of the PD bags are relatively limited or fixed, and depending on the patient prescriptions, as a result, because you can't kind of ask the patient to use a much larger bag while they can only use they are only needed like 1.5 liters of PD gels, for example. In which case, if they have a 2.5 liter bags, you have to discard 1 liters every time for exchange. So again, that's a lot of wastage. But again, during the conferences, some of the industry partners present at the conferences highlighting that it may be difficult for them in terms of the industrial point of view, as I will highlight later on in some of the final slides, that in terms of the manufacturing, that in order to standardize the different various size of the bags, and by offering slightly more variable choices, it actually may be quite difficult for them in terms of producing a more production lines, for example. So there again, there are a lot of controversy that we need to highlight, and certainly we need to discuss with the industry. And with that line of work, there has been procurement statements coming out from our group, the Green Case Steering Committee. So be on the lookout for that. Hopefully, we can kind of liaise with them, some of the industry partners, to kind of streamline some of the production process. And there also has been talks for one-way valve, in a sense that if the drainage bag, as you can see in the bottom here with the infusion bag with the drainage bag, whether we can simply remove the drainage bags to minimize the design, such that after the infusions of the bag, with a one-way valve, you can actually disconnect this bag and then change this into a drainage bag, for example, then save you having the need for a separate drainage bag. So modularity in designs has been kind of discussed. So again, a lot of these, as I will highlight later on in the directions of the research, that actually still require a lot of clinical studies, because it's very all good and well talking about some of the potential designs. There's simply no actual data that we can back it up. For example, biological safety in terms of peritonitis risk, for example. So there's still a lot of things we need to talk about. So with that, in terms of moving on, in terms of waste management as well, there are lots of these actually quite common sense in a sense. A lot of the participants have been talking about some of the potential innovations in terms of redesigning some of the packaging system, such as using a more reusable, washable tote bags to kind of pack some of the PD bags, for example. And redesigning the cardboard packaging such that they could be a much more easier folding for storage space and recyclability. And there are no actual examples from the PD world or HD world even, but just to highlight some of the pictures here, actually a lot of other products in terms of consumable industry, a lot of efforts have been put onto some of the packaging. For example, as you can see, along recycled boxes with a lot of inks, indelible inks that perhaps you can recycle because of that. And there's in plastic attached to it, and staplers, etc. that can be quite difficult to separate. And plastic wrapping, for example, if you can change that into much more of recyclable paper packagings, with some of the cushioning that have been designed using paper and paper wrappings with some of the different texture, for example, that may be helpful in terms of streamlining some of the recyclabilities of the boxes. And again, removing some of the kind of adhesive of the plastic staplers or the indelible inks, then perhaps that may be, again, improving the overall recyclabilities. And again, there have been talks about the plastic wrappings of the PD bags as well. Perhaps if we can change that with a design to kind of link it with the PD bags, or removing altogether, because if the initial PD bags in itself, the integrity is strong enough, then perhaps we don't need extra protective layers. So there have been talks about trying to minimizing some of these wastage or redundancies. But all in all, the participants strongly agree that even though we are talking about in terms of improving the designs, for those components that are not contaminated or in contact with bodily fluid, they should be recycled as a default. So hopefully then we should consider kind of, even as Katherine already highlighted some of the current practices, perhaps we can kind of segregate some of the waste usual PD or HD practices, and then hopefully then send them off to recycle. So quickly onto some of the slightly more innovative approaches as we're using some of the dialysis efforts. I'm sure you know the dialysates currently, in terms of the current practices, a lot of them will be discarded because there always has been the risk of highs in terms of salt or in contact with the potential patients, and as a result, infection risk. But actually, when you think about it, those dialysis efforts are relatively speaking high in electrolytes, but also high in uremic solid, which to a plant could be a very useful fertilizers. So there have been a lot of the discussions on how to capture these or we're using these efforts to further downstream in terms of potential applications. For example, there have been talks about incoming technologies such as optimizing the reverse osmosis machines with nanofiltration filters and try to produce some of the higher qualities of waters by removing some of the salts and contaminants. But again, currently speaking, there's still kind of research works because a lot of them can be quite energy intensive. So we are trading off one potential benefit with slightly more other problems. And again, biological safety must be verified for obvious reasons. And there are again a lot of redesigning discussions on redesigns and methods to try to perhaps offer much lower alternative to the nanofiltrations. There have been study on that, and again, participants felt that although it is attractive and certainly much lower energy in consumptions, it is much less effective in terms of desalination, removing some of the salt. And a lot of the paper quoting that is currently still only be able to produce a much lower quality in water, such as only for irrigations, for example. As I mentioned, because of the dialysis being high in uremics, solid and electrolytes, there has been potentials in terms of capturing that in the use of transforming them in terms of fertilizers. Actually, in fact, there have been studies in Middle East and try to highlight to use that some machines in terms of facilitating the conversions of those dialysates into steroids, which is actually one of the currently used slow-release fertilizers. And in fact, from their paper, they highlighted that the 20 stations actually unit in the center are able to kind of generate about 2.5 kilograms of steroids per day, and that's in fact was enough to fertilize 5 hectares of fields for fertilizing use annually. So perhaps we should start think about this further. But again, these are only pilot studies, and a lot of much larger scale data are needed. And as I mentioned, there has been talks about recapturing some of the heat energy, and actually in terms of changing some of the water pipe system may be quite helpful, because actually there has been again study highlighting that the discharge of those dialysis even at body temperature from an HD center into a sewage system, those wastage actually has been estimated as you can see a quite large gigawatts per hours of recoverable energies in terms of heat per year. So in fact, participants are also highlighting that those energy potential, for example, in Europe, are equivalent of heating 140,000 households. If, for example, if each household is about 12,000 kilowatts per hour, actually those per years, those energies per years actually can heat up 140,000 households in Europe. So actually signifying quite a significant waste loss that energy were being lost through heat. So by redesigning some of the piping works and recapturing some of the heat, you can actually we kind of convert those heat into other applications such as warming the household or warming the actual warming some of the water for heat disinfectant within the center, for example. And some slightly even higher works, there has been talks about piloting microbial fuel cells for generating a small amount of electricity by breaking down some of the organic matters. But again, these are very, very kind of forefront in terms of the research setting, and many years must perhaps will be needed to kind of validate these productions in terms of large scales, but also clinical safety, for example. So finally, on those few other settings, such as reverse osmosis, but there also the concept of forward osmosis, in which case you kind of readjust the circuitries and relying on purely kind of diffusions, in which case you try to as you can see at the usual out settings, you kind of have inlets of water, reversals, osmosis machines through energies, but also with higher pressure to try to reduce the purified water, but as a cost of the reject water, and then obviously downstream as usual to the patients, etc. But as you can see from the forward osmosis machine point of view, you're still relying on some of the inlets of ultra pure water. But afterwards, after in contact with the patients, and then those water becoming a spent dialysate, you could use this forward osmosis with an filtration filter with some concentration new dialysis through this work to kind of regenerate some of the dialysis through recovering of some of the water from the wastage of the spent dialysis. So with that, you kind of save some of the water and then you can reuse them. Again, the benefits of this is that it actually operates as a much lower pressures and energies compared to reverse osmosis machines, and hence less electricity use and less rejection water use, as highlighted from the usual reject water from our machines. But also actually the way the membranes are designed, actually there has been talks about the membranes being much less prone for fouling and potentially lengthening the requirement of the lifespan, and as a result lower maintenance per se. But currently there's no data to the moment in terms of actual clinical practice. We still have a lot of work to go through. For example, how to optimize the removal of the solids from the urea rejections, and then producing some of the higher quality of water. Because of the way of the membranes works, it's slightly more complex. That's obviously with the compatibility issue with heat disinfections or chemical disinfections. There's obviously the safety with infections, but also cost implications. So there has been also talks about sorbent technologies. Actually, there has been a lot of papers incoming, and in particular in the fields of PD, for example, sorbent technologies are kind of similar in the sense that instead of an actual dialyzers, you kind of have a sorbent cartridge that you can kind of link it with a patient, and with that you kind of have a closed circuitry to kind of to perform the dialysis, but also regenerate some of the required dialysate. And then that can feed back to the patients. And certainly that is very attractive because then you can reduce the usage of water. For example, there has been study highlighting that you could potentially reduce up to 99% of the water usage in some of the HD circuitry with using sorbent technologies, and at least 75 to 85% from the PD prototypes. So, but furthermore, you can actually reduce some of the potential plastic use, because then with sorbent technologies, then perhaps there could be the less transportations with PD fluid, for example, and reducing some of the consumables and transportations, and very attractively, then you can reduce a lot of carbon footprints and wastage. But again, there's a lot of key challenges from the conferences highlighting by a lot of participants. We still have to similarly, we still have to optimize some of the kind of efficiencies of the sorbent technologies, and in particular, try to minimize the overall size of it, but also in terms of patients' receptance. Again, a lot of the studies are very small scales, and we do need a lot of large scale studies in terms of highlighting the productions, but also the actual environmental costs. So they always, again, similarly talks of points of care PD fluid regenerations. Again, attractively, they reduce the transportations, but also the PD fluids, because then you can produce them on site. And then, in fact, there's currently two systems being designed and being undergoing trials. There has been talks of the first human trial, but I just heard from Katherine that the first human trials was supposedly underway in Australia, is currently installed, because again, it's highlight the challenges, because the receptibilities of some of the questions in terms of safety issues and the resources still requires a lot of evidence. So with that in mind, we still need a lot of validation in terms of the qualities of the dialysates, the safety of it, and the costing issue. So although it is very attractive, it's still on only in the pipe works. So finally, in the last two slides, there has been talks of the usage of bioplastics. I'm sure you know that both in terms of HD, but more so in PD, there are lots of usage of plastic, in particular PVCs, which is relatively very versatile and very chemically inert, up to the point that, however, it does actually have a lot of environmental concerns because there's also usage of chemical leakage and also toxic emissions from incinerations. So there are a lot of challenges. Using plant-based productions may be more attractive. But again, there's hardly any major large-scale data, so we still need a lot of life cycle assessment. And finally, with the transportation considerations, similar to consumables, actually transportations within the kidney care actually does generated a lot of carbon footprint and is a huge, large contributions. For example, patient traveling, but also supply chains in terms of transporting some of the equipment. There has been talks within our groups that remote patient monitoring may be attractive options in some particular settings, because in a sense you will reduce the traveling cost. The patients can visit your center much less in frequencies, and then enabling perhaps early intervention if need be, because then you could monitor them frequently, remotely. But currently, there's no data on environmental impact, so we do need some of the life cycle assessment. And there has been a huge controversy in terms of some of the productions, be it local productions of consumables or PD for bags, for example, but versus centrally. Because obviously there's the local production may be a benefits of resilience, because if one center is done locally, you still have some limitation productions, but obviously from an industrial point of view, a lot of the industry partner mentioning larger scales of production and would have a much better economies of scale, for example. So with that, finally, I just quickly highlight there are lots of things, lots of research and lots of innovations going on. And just to highlight a few here, but obviously that generated a lot of questions as well. And where do we go from here? So this is from the paper, but these are some of the questions and knowledge that we generated from the conference. Given the interest, I won't go into in details, but suffice to say, a lot of them still require clinical validations. And again, a lot of them, even though it's very attractive, we still have to validate in terms of the actual kind of environmental impact through actual life cycle assessment, because there may be hidden environmental costs, as for example, as I mentioned, for example, the use of AI. While it's attractive to streamline some of the processes, but there's obviously the cost of some of the energy levels. So there's still a lot of things we still have to go on. So with that, I thank you everyone for listening. I do welcome everyone to have a read at the paper, but also the recent publications of the ISN Green Dialysis Toolkit produced by the ELP group, but also Green Case Steering Committee. Thank you. I'll pass on to Katherine to kind of highlight some of the final slides on the KDIGO.
Thank you, Winston. Look, I just want to make the point very quickly before we open up to questions that academic conferences, scientific meetings are obviously really important for learning and knowledge sharing and scientific advancement, but meetings in themselves have a substantial environmental impact. And there is an inherent contradiction in the fact of holding an international in-person meeting on environmental sustainability. This was recognised at the outset, and to KDIGO's credit, it committed from the outset to firstly go to all possible efforts to minimise the impact of the meeting, also to map and then transparently report on the carbon footprint of the meeting, and to offset all emissions remaining after we'd try to mitigate as much as possible. We've detailed our findings in a paper that has recently been published. Obviously, this doesn't undo the impact of the meeting, but I think it's a really important first step that we start transparently looking at the impact that we're having and making sure that the meeting and the outcomes that come from it justify the impact that it has. And I think, we very much hope that in this case, the knowledge that was gained and the collaboration and hopefully the changes that will flow on from the recommendations in the report will lead to more environmental gains than the meeting had impact. So thank you, and very happy to take questions.
Well, thank you very much to both our speakers. There are a number of questions that were put in the chat, so I'm going to ask them to speak to a few of them. I also want to let the audience know that we probably will go over about 5 minutes. We can continue just a little bit after the top of the hour. This webinar has been recorded and will be available online. So for the first question, one of the things that's come in kind of in a couple of different flavors is how to think about the patient perspective on green dialysis. So first is, the lack of uptake of some of these strategies. Is this more of a patient acceptability issue, or is it a healthcare system problem? And then second, just kind of balancing this idea of a patient really just wants good dialysis and the best therapy they can get. How do we consider the patient perspective when we're thinking about making some of these machine or treatment modifications? Katherine, maybe I'll give you first stab, and then Winston, have you chime in.
Yeah, thank you. I mean, as I mentioned at the start, we had patients in attendance at the meeting, and their perspectives were really central to all of our considerations. I think that there are many patients that just want good dialysis, but there also are many patients that want environmentally sustainable dialysis. And the two things absolutely are not mutually exclusive. What we really highlighted throughout the meeting is that the priority has to be giving or providing good dialysis, but there are ways to make sure that is environmentally sustainable. I think very much patients should never be made to feel that the treatments that they're receiving are a burden, but the way it can be presented is that there are win-wins. You can have both. And very much at the system level, environmental sustainability should be part of the equation. Patients should not have to feel bad about the cost of their treatment, but at a system level, we consider it. It should be the same thing with environmental sustainability. One thing that really came out in the meeting was waste was a big issue for many patients, particularly home patients. So, thinking about the impacts of, or the environment, what the impact that the environmental impact has on patients is really important, and making sure that many of the improvements we try to make improve their experience from that perspective. And I suppose just to say, add in, my experience has been that there are very few patients that, resist changes in this field. If it's presented as improvement, which it is, improvement to the way the care is delivered, most of them are really receptive and encouraging and want to be part of it.
Thank you, Katherine. And just to quickly summarize as well, I think the key important is the engagement, but also communications between the different parties and patient included, because we certainly the important thing is, as Katherine highlighted, we want the first and foremost patient safety and also providing good dialysis. But within that context, what we can do to try to optimize and minimize some of the kind of environmental issue, and that's the key. So I think importantly, we need to convey that message to patients to let them know that we're not simply cutting the cost, but rather it's within the context of patient safety and acceptability that what we can do to maximize the environmental potentials. Because there actually, I agree with Katherine, with that kind of complications, a lot of patients will be more receptive in terms of some of the practice changing. But in the early days, I remember a few years ago, even across the world, they're having kind of patients groups statements highlighting their concerns about optimizing green nephrology, but at the expense of patient safety. And that was actually to my surprise, because there was a quite large patients group highlighting some of those concerns. So I hopefully with time now, with patient engagements such as the KDIGO conferences involving patients, that kind of notion can be changed.
Great, thank you to you both. Another topic that comes up often is how to consider this issue, particularly in resource-limited areas. So maybe Winston, what low-cost innovations do you feel like have the most potential for improving dialysis sustainability in those areas? And one of the questions in the chat relates to this, and they were specifically interested regarding reducing redundancy of consumables. Are there studies that show you can do this and how to think about implementing this in low-resourced areas?
Yes, thank you, Jenny. It's quite important question. First of all, we are very exciting about some of the newer technologies coming through. Obviously, even similarly with medication, for example, in order to kind of disseminate across the world, it can be quite difficult. There's still a lot of disparities. So in a resources limiting settings, I believe that there are things obviously that we can still do, as I highlighted and Katherine highlighted. There are some of the practice or current practice changing things as highlighted, for example, such as redundancies or consumable reductions. And so those are, relatively speaking, much easier to do and perhaps much more impactful as compared to a slightly fancier points of care PD generation machine, for example. So I believe that in terms of resources limited setting, there's still scope and potential that we can reduce some of the environmental cost. And regarding to some of the consumable use, there has been increasing papers trying to kind of tackle that. But as far as I remember, there's actually no major, for example, in terms of reductions of some of the consumables such as gauze, for example. The actual upcoming ISPD position statement, we have been discussing this as well, because this is more of an expert opinions and a position statement rather than an actual guidelines per se, that we believe that some of the usage of gauze, for example, can be limited to perhaps once per procedure, for example, in some of the specific settings. Obviously, we do need some clinical data and research on that. But I'm sure Katherine will supplement as well. There has been talk against, for example, incremental PDs that dialysis or that we can practice, and that actually already would be very helpful in terms of reducing some of the kind of resources usage. So there are things that we can certainly do, but again, a lot of them are still needing a lot of actual clinical validations and life cycle assessment to kind of really pinpoint the benefits of the environmental impact per se.
Another question that's has come in from a technologist in Canada, appreciating the fact that reducing the dialysate flow rates not only lowers water consumption, but also reduces the acid concentrate use. However, they appreciate that this requires modification to the RO settings and talk some about the need to optimize RO settings and also the consideration of using central acid delivery as opposed to jugs. Katherine, can you comment a little bit about your experience with some of the ways to optimize RO settings and thinking about some of the differences, particularly with the older versus newer models of ROs?
Yeah, so I think if you're looking head to head at environmental gain, optimizing RO plant functioning is really where the money is. So it is by far the biggest user of power and water in a dialysis unit. And so, relatively speaking, reducing dialysate flow rates won't have as big an impact. In terms of the newer RO plants compared to the older ones, they have all sorts of features that conserve energy and water. So things like you can adjust recovery ratios depending on the quality of the feed water. You can, the newer systems can recirculate unused permeate. They use different disinfection technology, which is more energy efficient. The issue with the more modern ROs, obviously, is that they come at significant capital cost. But when it's time to upgrade an RO, certainly looking at the extent of the newer features and the impact they have on resource usage is really important. There's a unit, I suppose, from a very simple perspective with ROs, not upgrading to a new one, but looking at the settings you've got are really important. So there's a unit in Australia that reported some data recently where they looked at when the RO was on compared to dialysis treatments, and they modified the settings, and they found that simply by turning off the RO earlier, not having it operating on a day when there wasn't dialysis, they cut power usage by about 50%. So, very often these systems run in the background without sort of close examination. As I said, the same with disinfection schedules. So just looking really closely at the settings that you have and what the plant is doing can make a really big difference. And then when it comes time to get a new machine, if the capital funds are available, then looking for the best options that are there.
So there are two specific questions, and I think we'll close with these. I'm going to read them both, and Winston and Katherine, I'll let you pick which ones of these you'd like. So the first one are there special techniques for extraction of struvite from spent dialysate? If so, can this be done in lower middle income countries? And then the second question is, how long does it take for a dialyzer to biodegrade? Do either of you know the answers to either of those?
Well, maybe I'll start off regarding the stir-fights. From the paper actually published in I believe it's in Morocco, they were highlighting the usage of these machines to kind of process the spent dialysate into stir-fry. So you do actually need some, relatively speaking, equipment. I believe it's like a filtration kind of machines that they can link up with the HD's circuitry. But apart from that, they did mention there from the paper, they also mentioned the kind of turnaround costing issue. And actually, as if I remember correctly, the costing kind of the returns is actually not that long. I believe it was a few years, and then you can already kind of regain the potential initial installations costing. And with that, you do have obviously attached with it some of the environmental benefits in terms of using those fertilizer as needed for environmental use. So I believe this potentially could be done in lower income settings. The paper was published in Morocco, and but again, as I mentioned, it's a very small scale study. It's only involving a single center at 20 beds. So we still need some larger scales, productions levels to see whether actually, generally speaking, whether it's feasible.
I'll take the one about the dialyzers. So, essentially, conventional plastics don't biodegrade in any meaningful time frame. They will eventually sort of fragment and break down into microplastics, but they won't biodegrade. So I think data I've heard about PET bottles, which are just the standard plastic water bottles, they take about 450 years to disappear. So I think we should assume that dialyzers are in the environment for a long time.
I want to thank both of our speakers for their excellent talks and responses to the questions, and thank you to everyone for tuning in to this joint ISN-KDIGO webinar. We hope you identified at least one action that you can take now to reduce the environmental impact of dialysis. If you'd like to learn more, we encourage you to check out the resources again on the ISN Green K website and read the KDIGO conference's summary that was published in Kidney International, as well as its companion paper that was published in Kidney International Reports. So thank you again for your time.